Hello everyone. Last class we discussed the derivation of three moment equation. What we will be doing today is we will demonstrate that derivation, demonstrate that concept through some examples. Let us take our first example. So, this is today's class is three moment equation and examples. Let us take the first example. This is a continuous beam, three span continuous beam A, B, C, D subjected to the loading condition that is shown here. Flexural rigidity of all the EI is constant for all this member A, B, B, C and C, D. Flexural rigidity is constant. We will see some more example today where flexural rigidity is not constant. Okay. Now, this is an indeterminate structure, and what is the degree of indeterminacy? We can see that that Ns is equal to 2 reaction at this reaction and this reaction, because if we remove support B and C, it becomes a simply supported beam, which is a statically determinate structure. Now, the presence of B and C, support at B and C make this structure statically indeterminate. So, Ns is equal to static indeterminacy is equal to 2. Now, okay. Now, let us then start this example. Okay. Now, you see first part of so the example is like this, right. This is the three span beam, which is AB, this is A, then a roller support here, another roller support, and then another roller support here. This is A, this is B, C and D, and this is subjected to uniformly distributed load on span BC, which is 7.5 kilonewton per meter, and then at midspan of AB there is a concentrated load which is 20 kilonewton. Okay. And these are all are 3 meter, 3 meter, 3 meter. These are the midspan 1.5 meter. Okay. Now, the first step is if we assume that there is a hinge here. If you see, we assume that there is an hinge here and there is a hinge here. So, by inserting hinge, we are actually releasing the moment constraint at B and C, or rotational constraint at B and C. So, static indeterminacy of this problem is 2. So, we insert one hinge at B, release one constraint, and another hinge at C, release another constraint. So, now this structure after inserting two hinges at B and C, this structure become statically determinate structure. This is hinge, internal hinge. Okay. Now, so we insert one hinge here at B and another hinge here at C. So, essentially it becomes AB, BC and CD, they all are simply supported. We can treat them as simply supported beam. Okay. Now, let us find out the bending moment diagram for this structure. Bending moment diagram is, if we see for span AB, which is subjected to a concentrated load at the midspan, and the bending moment becomes, bending moment is this, and then for span BC, which is subjected to uniformly distributed load, bending moment, we know the bending moment is parabolic, it is like this, and for span CD there is no load, so there is no bending moment. So, for span AB, if we know span AB is which is concentrated load 20 kilonewton, we know that bending moment will be bending moment this is 1.5 and this is 1.5 meter, and we know the bending moment at this point will be WAB by L. In this case, A is equal to 1.5, B is equal to 1.5, W is equal to 20, M is W AB by L. A is equal to 1.5 meter, B 1.5 meter, L is 3 meter. So, this becomes 15 kilonewton meter. Okay. And similarly, if you take span BC, I am not writing the detail of this expression for bending moment, because we know how to do it. Then for span BC, which is subjected to uniformly distributed load, this is AB, this is BC. BC, we know M is equal to, if it is W, then W L by 2 x minus W x square by 2. That is the expression for bending moment, and bending moment is maximum at the mid span, and that value is W L square by M max is equal to W L square by 8. So, L is equal to 3 meter, W is equal to 7.5 kilonewton per meter, and then this value becomes 8 point, this value becomes 8.4375 kilonewton meter. I am not writing the unit here. So, this is the bending moment diagram for this. Okay. Now, if we see the equation for 3 moment, the equation is this, right. Now, since EI is constant in this case, so these values are, these are all constant, these are all constant, these are all constant. Okay. Now, first let us apply 3 moment theorem at B. 3 moment theorem at 3 moment equation at B means consider the span AB and then BC, get some equation, then we apply the 3 moment equation at C, means considering span BC and CD. Okay. Now, from this from the configuration and the support condition of this structure, we can say that moment at A and moment at D is equal to 0, right. So, MA is equal to 0 and MD is equal to 0, because the at this it is pin support at that point. Okay. Now, so we know that MA is equal to 0, MA is equal to MD is equal to 0, right. Now, in this equation, in this expression, and if you remember, AB is the area of bending moment between A and B, and ABC is equal to area of bending moment between B and C, and XAB is the distance of centroid of that bending moment from A, bending moment M by I diagram from A, and XCB is equal to the centroid of bending moment diagram between B and C, and this distance is measured from C. So, let us now first determine what is AAB, and this is then area AB, this is the area AB, and this is the area BC, area BC. So, area AB is equal to half into 15 into 3 is the then this become 22.5. Okay. Now, and then what is area BC? Area BC, that is equal to this area of this 2/3 into this value 8.4375, and then into the length 3, which is 16.875. Okay. So, this is area AB. We will be using these values, and this is area BC. Okay. So, we need to find out what is XAB. XAB is equal to XAB, which is the centroid of this diagram from A. So, this is symmetric, it is 3 meter length. So, XAB becomes 1.5 meter. Similarly, XCB it is area, it is centroid of this bending moment diagram from C, again it is symmetric. So, it becomes 1.5 meter. So, this value we have already obtained. Okay, already obtained. So, this is A, B, C, D. Okay. Now, let us apply the 3 moment equation. First apply 3 moment equation at B and then apply 3 moment equation at C. So, first apply 3 moment equation at B. Okay. So, 3 moment equation at B. 3 moment equation at B. Now, what is the expression? Again, if I write the expression, general expression for 3 moment, EI is constant, there is no support settlement. This expression becomes MA LAB plus 2 MB into LAB plus LBC plus MC LBC is equal to minus 6 AB into XAB by LAB minus 6 ABC into XCB by LBC. This is the 3 moment equation. We know this, right? Now, if we apply it, then what we have is there is no EI by EI term, because the flexural rigidity of all the span this is constant. Okay. Now, what will be LAB is equal to 3 meters. So, this become 3 into MA, then plus 2 MB. LAB and LBC all are 3 meter, plus 3 plus 3, and then plus MC into 3 BC, LBC is equal to 3 MC, that is equal to minus 6 into AB, and if you remember AB we have determined this is 22.5 and BC is 16.875, that is already determined, minus 6 5 into XAB, again XAB is 1.5 and XCB is 1.5. So, it is 1.5 and the length is 3, and then minus 6 into 16.875 into 1.5 by 3. So, this become 4 MB plus MC is equal to minus 39.375. You can do this calculation. Okay. So, this is equation number 1. Okay. So, this is equation number 1. So, we have a relation between MB and MC, and that relation we obtain by applying 3 moment equation at B. Now, let us apply. So, let us apply now 3 moment equation at C. If we apply 3 moment equation at C, then the expression becomes, similarly, if we do the same exercise, the expression becomes at C, this expression become 3 MB plus 2 MC into 3 plus 3. When we apply at C, means we have to consider, when we apply at C, then we have to consider span BC and CD, means MB, MC and MD will come into this equation. Okay. And then plus 3 MD, okay, and that is equal to minus 6 ABC, ABC means 16.875 into 1.5 divided by 3. You check here, since there is the bending moment between C and D is equal to 0. So, therefore, on the right hand side we will have just contribution from this only for the span BC. Okay. Now, we we have already written here that MD is equal to 0 because it is simply supported end. So, it is a hinge support we have at there. So, MD becomes 0. So, here MD becomes 0. If MD is 0, then finally, the equation becomes 3 MB plus 4 MC is equal to minus 16.875. Okay. So, this is the equation number 2. This is equation number 2. Now, this equation is another relation between MB and MC. Now, we have two equations and number of unknowns are 2, MB and NC. We can solve them, and if we solve them, the values that we get is this. MB is equal to MB is equal to you can I am not solving it, I am just writing the final result 375 kilonewton meter, and MC is equal to minus 1.875 kilonewton meter. So, two redundant forces were MB and MC, and these redundant forces, the values of these redundant forces are these, and we obtain these values by applying 3 moment equation at B and C. Now, once we know the moments at B and C, then rest of the thing is just take the free body diagram of different parts, apply the equilibrium condition, and get the other forces. And we can do that. Let us draw the free body diagram of MB of the actual structure, because now we have already obtained the values at MB and MC. Now, we need to find out the reaction forces of the actual structure, not for this. So, actual structure is this. A, B, C, D, and then we have force, and then our reaction like this. This is 7.5 kilonewton per meter, and this is 20 kilonewton. Let us draw the free body diagram of AB. If we draw the free body diagram of AB, then these will be the reactions AY, AX, and then BY and moment MB and concentrated load 20 kilonewton. Okay. I am not writing Fx here because we assume that there is no axial deformation. Now, apply summation of say MB is equal to 0, moment about B is equal to 0, this is A, this is B. What are the moments we have? We have minus MB, which is anti-clockwise, so negative. Then AY will contribute, and then AY will be AY into 3 is the length, and AY produces clockwise moment, and then finally minus 20 into 1.5, this will produce anti-clockwise moment, and that is equal to 0. MB already we obtained this MB. If we substitute M, then MB in this equation we will get AY is equal to 875 kilonewton. Okay. Now, this is AY. Now, similarly, if we take free body diagram of CD, if we draw the free body diagram of CD, and then what are the reactions we have? We have support reaction dy, and then Cy and MC. Okay. This is C, this is D. Now, take MC is equal to 0. If we substitute MC, if you take moment about C is equal to 0, only forces will contribute dy and the MC, the value of MC already known, and we can get the value of dy. dy will be minus 0.625 kilonewton. So, similarly, you can apply, once we know similarly you can take the free body diagram of other parts, apply the equilibrium equations and get the other unknown, because with the knowledge of bending moment at B and moment of C, now the structure become determinate. All the other reactions forces or the internal forces that can be determined just by applying the equilibrium conditions. Okay. So, rest of the things are very straightforward, you can continue with that, you can compute the results for this. Okay. Now, if we have to finally draw the bending moment diagram of this. Okay. Now, let us draw the bending moment diagram. Bending moment diagram of this will be, now you see, since the linear superposition is valid, so bending moment diagram will be, this bending moment is assuming there is a hinge at B and C by releasing the redundant forces, and then so this is a primary structure which is subjected to only the external loading. Then there will be another primary structure which is subjected to only the redundant forces. So, total response of the structure will be the response of the primary structure subjected to loading plus the response of the primary structure subjected to the redundant forces. So, total bending moment will be, or bending moment diagram will be, this bending moment diagram plus the bending moment diagram that you get because of this redundant forces. Okay. Now, there are two ways you can draw this bending moment diagram. First is the bending moment diagram due to the, let us draw it here, so that it is. So, first the bending moment diagram due to the redundant forces. So, this is A, B, this is C and this is D. And then, okay. So, this value is 15 and this value is, we know that 8.4. Okay, and there is no bending moment at C. These are all positive bending moment, right? Because the way it is, we take the sign convention, according to that these bending moments are positive. Now, then we have MB and MC are negative, and then support moment at A and moment at D, they are 0 because it is hinge support. So, MB is negative and this value is minus 9 point something. So, it is negative. So, this value is minus 9 point something, and then at C it is minus 1.875, and then your bending moment for the redundant forces become this and this. Okay. Now, you see, so this bending moment on this is this part will be cancelled, then bending moment on this will be only this part, okay, only this part. This will be the bending moment on this, and the values will be, this is positive, this is positive, and this is negative. This is also negative and this is positive. This is one way you can show the bending moment diagram. Now, another approach, I personally prefer the second one, this approach. You draw the entire beam. Okay. As per according to our sign convention, we draw the sagging bending moment on the top side and hogging bending moment at the bottom side, right. So, we always draw the bending moment as per our sign convention. We are drawing the bending moment in the compression side. Okay. So, now first draw the negative bending moment. Negative bending moments are MB, it is at MB it is minus 9 point something, and at MC it is this value. So, negative bending moment is this. Okay. Then, since the superposition is valid, so total bending moment at any section will be bending moment due to the external load plus bending moment due to the redundant forces. Now, the bending moment due to external load is this. You draw the bending moment at A is equal to 0, at B it is 0, at this point it is 15, but at this value is 9.375 and this is 1.875. They are all negative values. They are all negative values. So, at the mid span it will be minus 9.375 divided by 2. So, at the mid span bending moment due to the primary load is 15 and the redundant force is this divided by 2. So, the bending moment is somewhere here. Okay. Now, and then at point B, bending moment due to external load is 0. So, at point B mainly bending moment whatever we have, that is due to the redundant forces, which is this value. Okay. So, this value and then this value. Then again go to C. At point C, the bending moment is it is 1.875, and similarly for external load, the bending moment at C is equal to 0, and it varies for the external load, it varies quadratically, and then this varies quadratically. Okay. And between C and D there is no bending due to the external load, it is only the redundant forces. So, the bending moment for this become this. The advantage of writing the bending moment, drawing the bending moment like this is, again you do not have to mention the sign like this. It is always understood if it is because our sign convention is we are drawing the bending moment on the compression side. So, it is the sign, just by looking at the bending moment diagram we can understand the sign. Okay. So, this was the first problem. Now, quickly let us see what happens if the condition is slightly different. Now, this is the deflected shape of this problem. We know the bending, we have just now drawn the bending moment diagram, and this will be the deflected shape of this problem. This deflected shape is not the actual, it is the normalized deflected shape, scale deflected shape. The idea, main thing is to have an idea about the deflection of this beam. Okay. Now, see, the important thing here is we assumed that in this example EI is constant throughout this length, right. But actually EI may not be constant, and if there is no, if that is not constant, then how to take that variation we can take that variation in the 3 moment equation itself. Then another condition where suppose in this example we have seen the structure is the response of the structure is mainly due to the external loading. Loading is being applied in the form of some distributed force or distributed moments or concentrated force and moments. But as we have seen in the last class, the external agitation may be given to the structure in the form of settlement of the support. Okay. Support may displace, and that displacement of the support may induce stresses in the beam, bending moments, shear force in the beam. Okay. So, next example we will see is 2 examples, the same example, but we slightly change the example by first thing by considering EI is not constant, and then in addition to these external support we will see that if one of these support they settles, then what happens to the deflected shape and bending moments. Okay, that we will discuss in the next class. Thank you.